We were talking about graphs last time. We talked about some more about what graphs are, but we also talked about searching graphs. We talked about what breadth first search and depth first search look like in a graph form, and we found that there were some times when searching the graph didn't really work too well for us, and that's if there were negative weights or if there were cycles in the graph. There could be, especially if there was a negative weight cycle, that was especially bad for something like finding the shortest path to a solution using a searching algorithm, because we could basically come up with the cost of negative infinity by never terminating and reaching the destination. We could always improve on that by going through that negative weight cycle. So those were two assumptions that we're running with when we talk about Dijkstra's algorithm, is that we don't have negative edge weights, we don't have negative cycles in the graph. In fact, we can't really have much of a, no negative weight can be in a cycle. So Dijkstra's is most similar to breadth first search. It really is just a modified breadth first search to account for the fact that we have weights. Breadth first search was saying that we're going to look at all of the edges around our starting vertex and then continue to expand outwards. But the method that we are using to evaluate how far away something is just by the number of edges that it takes to get from here to there. Rather than the number of edges, now we are going to use the cumulative edge weight. And it basically is a breadth first search using the cumulative edge weight, except that rather than being at a current vertex and looking outwards, we're going to have a kind of a horizon, a list of visited nodes that we have been to, and all of the nodes that are connected in some way to a node that we have visited. And we will be intelligently selecting which node or vertex to visit next based on the edge weight from our source, including that edge. So we're going to take the minimum edge that allows us to explore a new node, cumulative edge from the source to that new node. So because of this, we can't use just a queue. We have to use a priority queue, which of course uses a heap underneath the hood. We talked about this as one of the many applications of heaps, but using a priority queue, you can now remove the vertex that is going to be the next one to visit based on that cumulative edge weight from the source to that vertex. So we're going to keep a set. I'm actually using this as a mathematical set here, so we can instantiate a set and use them. A set of visited nodes. And once we visit a node, we know the shortest path to that node. So every loop through, we are going to be visiting a new node, determining if there are any new nodes that we could not have got to before, but now we can because of the new node that we explored. We're going to add those to the priority queue and then loop around. So nodes that we haven't visited yet are going to store something as well called the best distance calculated so far, that we don't yet know if it's the total shortest path to that node, but it is the best one through the nodes that we have visited so far. Once we visit new nodes, we may find a new shorter path to that node. And then once we visit a node, we can also call it expand a node. Once we visit it, we know the optimal path for it. There are no new ways that we will explore a new path to that node. Once we visit it, we know for sure that the shortest path has been calculated. By the time the algorithm finishes, we know the shortest path from a single starting point to every other vertex in the graph. So this isn't a one-to-one, we actually get a one-to-many for the same cost. So maybe we set A as our source node. By the time Dijkstra's terminates, we will have the shortest path from A to every other node in the graph. We could then run Dijkstra's on B, and we would get the shortest distance from B to every other vertex in the graph. So we need an all pairs shortest path. There's actually an algorithm that is better than repeatedly running Dijkstra's. You'll learn about that eventually, but let's talk about it. So we'll start out by talking about this set of visited nodes, and we're going to call that set of visited nodes the cloud. So the initial state, we know that we passed Dijkstra's a starting node. We know that that node has cost 0. we are going to initialize every other node in the graph to have cost infinity. Just because we don't yet know how we're going to get there. Until we know at least one way to get there, the best way that we have so far is going to have cost infinity. We have not considered any edges yet. So that's initializing Dijkstra's. Then we will loop the following. We're going to pick the closest unknown vertex. So when there's only a single vertex, we're going to be looking at all of the neighbors of that vertex and ask which one of those has the shortest edge cost. We're going to add that to the list of known vertices and visit it. So you can also think of it as adding it to the cloud. We then, once we visit that node, update our list of edges that allows for determining if we can get to a neighbor of the node that we just visited that's also a neighbor of something that we've seen before, but that has a better cost or a shorter path. So let's give you an example. Here's something like the cloud. If you want to visualize it as a cloud, we would start here by saying, okay, A has cost 0. Everywhere else has cost infinity. We want to find the shortest edge out of A to something else. We see that we can get to B with cost 2, to C with cost 1, and to D with cost 4. You throw these in a priority queue, a min heap, and you extract the minimum value, which is going to be at the root of that priority queue. And you see that with cost 1, we can get to C. So we are going to visit C first as the vertex that has the shortest path from A. We now know that since we have visited C, this is the shortest path to C from A. If there were a shorter path, we would have explored it already. If there were a cost 0 to B, 0 to C, we would have explored the cost 0 to B before we explored the cost 1 to C. Because we visited that, we know that the shortest path to C is through just the direct connection from A to C. We explore C, and now we're going to add additional costs to any node from C that we can get to from C. The only one we can get to is E, with cost the 1 we've already seen to get to C, plus the 11 to get to E. So we are going to update the best cost we've seen as a way to get to E as 12. We have not explored E, we are not exploring E at the moment. We're just saying it's a neighbor to something that is currently in the cloud. So because of this, we're going to store, if we were to go directly to E from somewhere we visited, that would be the cost. If that ever becomes the minimum cost of all of the associated edges in our cloud, we will know that that is the best path. But until we get to that point, we don't know that for sure. Next, we look for the minimum total path cost from anything adjacent to anything in the cloud. The cloud now contains A and C. So that's going to be B. We can get from A to B with cost 2. When we reheapify our heap, that root, that minimum cost is going to be the 2 going from A to B. So we will visit B, add it to the cloud, and look where can we get from B. We can get from B back to C with cost 2 plus 5 is 7. Since 7 is greater than 1, we ignore it. We're not going to explore that. We can get from B to F, a new node, with cost 2 plus the cost that it took us to get to B, which is a total of 4. And we can get to E with cost 10, which is 2 plus 10 is actually equal to 1 plus 11. So we can store either of those. You can break that tie however you like and say the best way to get to E found so far is either through B or through C. Does not matter. So now we have a cloud of A, B, and C. The minimum now is a tie between the cost 4 to get from A to B and the cost 4 to get from A to B to F. You can break that tie however you like. We're going to assume we break it with D because things that are earlier in the alphabet are going to be what breaks that tie. So the node that is D will be explored first. We explore that and we ask where can we get to from D? Well, we can get to E with cost 7 plus 4, which is 11, which is better than the 12 that we've seen so far. So we're going to replace the best way to get to E from whether it looked back at C or B, those were a tie. Now we will look back at D as a way of saying, okay, we can get there now with cost 11 instead of cost 12. We can also get to C with cost 2. 4 plus 2 is 6, which is worse than the 1 we have already from A. So we're going to ignore it. We just continue this process until we visited every node in the graph. There are questions about kind of the basic sequence of actions that we are taking. Diving into some pseudocode. Looks something like this. For every node that's not the source node, we're going to set the cost of that to infinity. And whether it's visited or not, do we know that we have a shortest path for it? We set that to false. We do not know the path from the source node to any other node. The source's cost should be set to 0, and we should visit the source. Then we hop into the loop. While there are still unvisited nodes in the graph, we're going to select some unvisited node with the lowest cost. So we're just going to remove from the heap. We get a node from the heap that is the shortest path cost so far. We're going to visit that node. For each edge out of that vertex, we see VU. V is the known vertex. So that means that V has to be the source. So for each edge out of that source, we are going to, with some weight, we're going to look at the cost of the best path to that. And we're going to say, okay, that is one cost. We have the cost to get to basically the cost to get to V plus the edge weight. The best path that we had found prior to that, and then we're going to, if we've found a new better path through this node that we just explored, then we're going to overwrite that to say that the cost to get to U is now the cost through V because it is better. By exploring this vertex, we found a better path to that node, so we should update the best cost that we've seen so far for that node. And we'll do that for every edge out of V. Let's go through and do it. So here's our first example. This looks very familiar. But when you set up something like Dijkstra's, usually you try to fill out a table like this. So we have the vertices A through H. Visited is, or known, is a Boolean. It's either true or false. We're going to set initially, I'll just start this up. We're going to set the cost to 0 and everything else to infinity, which when displayed here just kind of looks like we don't know yet, but mathematically we're just storing it as a number that is so large that it's not feasible. So we set A to visited or known, and now we can kind of fill that in as green, and then any edge that we have from A outwards, we're going to fill in the cost. We don't know for sure whether the cost to B is 2, C is 1, or D is 4 yet. So we're going to basically throw in this less than or equal to say this could be the best path, but we haven't proven it so far. And then the path is just a backwards arrow pointing to which vertex did we come from to achieve the cost that is currently in the cost column. So the source of that was through A, which will allow us to reproduce a path once we know what the shortest cost is. So go ahead and take a second and fill out the rest of this. And we'll see if your answers and process match with my answers and process. Feel free to work in groups. making sure you're on the right process or thinking the right way. Here's after the second pass. How are we doing? Anyone have an answer yet? Build out table, I should say. Give you a little bit more time. Anyone stuck and not know how to proceed? That's okay too. Well, I was starting to describe this, but let's go through it in a little bit more detail. So we can query the cost column and say basically what is least that is unknown. So you're looking for that less than or equal to in the cost column. So what is the lowest number that has a less than or equal to associated with it? That is B with cost less than or equal to 2. You find that minimum cost and we're going to visit it. By visiting it, we explore E and F. There's no better path to E, so we're not going to replace it. That's how we're breaking the tie here. We're not going to replace something that we see as a tie. And then we add a path to F that is less than or equal to 4. The cost to get to B plus the cost from B to F. And you see that the cost to get to B is now stored in the B's cost column. So you don't have to do any adding up of edges. You just do a reference to the table. Now we've explored everything adjacent to B, so we're ready to loop back around and ask of everything in the table, what is the minimum cost with a less than or equal to applied to it? We see that that is D and F, so we're going to bias that by saying D. We explore D, we finalize that cost for in the cost column. From D, we can't hit anywhere new. We check C, but sure enough, that 4 plus 2 is not less than the 1 that we've already found to get there. So we make no further updates. We loop back around. What is the smallest cost with a less than or equal to in the cost column? It's F with cost 4. So we're going to expand that and see that we can now also get to H. We put the back path there to B to say, how did we get that 4? Well, we went through B. So if we want to be able to reproduce the cost 4, we just look backwards to the path B, go backwards along that arrow from F to B and see that that edge weight had cost 2. We could have figured that out too if we looked at the cost to get to B and took the difference of 4 minus 2 was 2. And that back path was through A, so we would then backtrack from B back to A. That allows us to reproduce the path of how we got to F. We see now that we can find a way to H with cost 7. That is now the smallest cost when we loop back around. So we're going to do that. We're going to expand H next. When we expand H, we see that we can get to G with an additional cost of 1. So we can update the G cost column to less than or equal to 8. And that's the only place we can get to from H. So now we again look at the cost and see less than or equal to 8 is the smallest. So we're going to expand G next. That 8 gets finalized. And when we go through G, it turns out that there's a better way to get to E. We'd seen less than or equal to 12, but now we see less than or equal to 11 going through G. That's cool. I did not notice before that the D to E was backwards. My bad. There was no 11 cost to get to E from D, but there is an 11 cost to get to E through G. And if we wanted to reproduce that path, since now we're going to expand and explore that and finalize it, this causes termination. But let's say we wanted to reproduce the path of how we got to E, the farthest node away from A, according to this graph. We would look at the path to E goes through G, costs 11. So we backtrack through the arrow coming into E from G. Then we do a lookup at the G row and see that we came through H. So we're going to take the arrow in reverse back to H from G, then look at the H and we see that that came through F. We go back to F and see that that came through B. We go to B and we see that that came through A. So we can reproduce the entire path of how we got to E through just referring to the path. And if we ever want to know what the edge weights are for that, rather than look them up, we can just subtract the cost when we do that from each other, and that gives you the edge weight that we saw. Questions on Dijkstra's or this process? Show of thumbs, how do we feel about it? We feel like I understand what's going on at this point. Kind of, sort of, not really. Okay, luckily we have another example. But let's talk about it a little bit in general first, and then we're gonna come back to a second example. So when we mark a vertex as known, we know the shortest path from the start to that vertex. But we also just went through an example of following the back pointers to get back to where we came from so that we can recreate the path from the table. When a vertex is not known, it may be that there is a shorter path that we find later on. We saw this when we explored E going through G. The entire time we had thought the shortest path that we'd seen so far was 12. And it turned out that by waiting until we explored a bunch of other nodes, we could find a shorter path, even though it was longer in terms of the number of edges. And that's when we see this kind of behavior, is when we end up with a path that is through a lot of edges, or more edges than the minimum number of edges, but it has a shorter total path cost. So that gets updated in later iterations of the table. So we already did this. We backtracked to get from E back to A by looking at the table. So let's dive into the second example. We want to find the shortest path from A to everything else. So we set the table up as such. Since the source is A, We set the cost of A to 0. We set the cost of everything else to infinity. And we start by visiting our source. When we visit our source, we mark it as known. We set the path to, it doesn't matter, not really itself, but it is the source. So it's the one vertex that doesn't need a path. We didn't arrive at A, we started at A. But we need to figure out everywhere we can get to from A. What vertices can we get to from A? C and D. So we're going to fill out that we have possible paths from A to C and D. So the first step is to visit A, set the costs of everywhere we can get to from A to those path costs, and then set the path for each of those from where we came from. The source of that edge was A. The source of the edge from A to C is A, so that's what we put in the path. The source from A to D with cost 1 started at A, so we put A in the path. And now we just go into that loop. We have now done the initialization steps, so we just loop until we are done. So go ahead and take a few minutes and see if you can fill this out. Let's start with, where do we first visit? D. Did everyone see why it is D? What other information do we need to fill out once we see that D is going to be the next place that we visit? There are a lot of places we can get to from D.
It's the costs you get from like D to B or something.
Yeah.
D to B to D to E.
Yeah, so we can get from D to B. So the cost to get from D to B is the cost so far to get to D, which is now 1. We're going to add 1 plus 5 is 6 and compare that to this value here. Since that is not less than 2, we don't update it. From D to E, it used to be infinity, but now we can get there for the cost to get to D1 plus the cost from D to E, which is also 1. We're going to update this cost to less than or equal to 2 with a path through D. We can update G. Current best is infinity, but we can get there from D. Cost to get to D is 1 plus the edge weight from D to G is 5. So this cost will be less than or equal to 6. And this will also path through D. We can get from D to F. Cost from infinity will go cost to get to D1 plus the edge weight from D to F is 6. So the cost to get to F will be less than or equal to 7, pathing through D. So that's everything for the next update. I guess we couldn't have gotten to B before. I keep seeing these arrows as backwards. So we do update that one as well. We can get everywhere from D. And this is a great example of somewhere where if you don't know that these are less than or equal to's, you might terminate here and say, we can visit everywhere with that associated path. But what is an example of a path that is wrong on here? If we just set these costs final and said, we're done. Where would at least one mistake be? Yeah.
I mean, getting to B right now it's 6, but you could go A, B, E.
Yeah. If you go A, D, E, B to get to B, that's cost 3, but the current best to B is 6. So shorter paths do exist. But we cannot finalize this until every less than or equal to is finalized and every vertex has been visited or is known, however you want to state that. What do we do next? Yeah. Go to C. Yeah, we're going to query this cost for anything that is not visited that has a minimum cost. So we can start with C. If we visit C, what does this change? What gets updated? Yeah. Yeah, so we're going to finalize this as 2. set it to known. But we need to look at everything that is adjacent to C. We can get back to D, but since we visited it already, there's no reason to even consider it. It first has to be unvisited and have a better cost than what we've seen so far. But getting to F, on the other hand, the cost to get to C, which is going to be finalized as 2, plus the edge weight from C to F, which is also 2. 2 plus 2 is 4, which is less than 7. So we're going to update that value as we finalize C. We also have to set that back path as going through C as the way we got this for. This will help us recreate the path if that turns out to be the optimal way to get to F. What's next? Expand E as the lowest cost in this table. We're gonna do that. What happens when we do that? We expand E. Do we see any other changes? We're gonna finalize 2, say that it's known. What else changes? Path to B. Used to be 6, but now we see that we can get there in 3. We're gonna do that. That changes the order we were gonna visit things, funnily enough. It looked like we were gonna visit F next, but because we've got a nice path to B, it actually becomes the next node we're going to expand and visit. So we're gonna do that. As we expand B, anything new? All of its neighbors are already visited, so nothing's going to update there. We just know now that that 3 is finalized. We can then expand F as the next smallest cost. We can find a way to get to G that's the cost to get to F, which is 4, plus 10, but that is certainly not less than 6. So we're not going to update G, so we visit F, and then we visit G. No further updates are needed, and now that the table is filled out, we are done. We terminate. And in this table is the shortest path and a recreatable path from A to every other vertex in the graph. Does that make more sense than it did before? How are we doing? We feel like we understand the algorithm a little bit better? Maybe? That's what a third example is for. But I also want to show this one because it's kind of fun. So rather than building up the exact table, we can just now, I think that we understand it just a little bit better, think about how Dijkstra's would work on this. So best cost to Y. Imagine we're trying to get from X to Y. What is Dijkstra's going to do?
First gonna visit the node to the right of X.
Yep. How about the best cost so far that you can imagine the cost being less than or equal to a value? How does that change over time? So it starts out when we look at X, we see that a neighbor to X is Y with cost 90. But as Dijkstra's evolves, what are those best costs so far values as we update them? Yep, that's exactly right. So we start knowing that there's an immediate neighbor, but since that neighbor to the right costs 1, we're going to expand that node first in case there happens to be a better path to Y through that node. And sure enough, there is. But there's also a path to a node to its right. So we're going to expand that first because the total cost of 2 is less than that of 81. And you can see now how Dijkstra's gets around the immediate paths to nodes by being able to path around them and eventually hop over once we know for sure that no better path exists. Question that I have now, how expensive is this? How many times are we visiting each edge? We're asking a question about each edge at most. Yeah. Yeah, once, right? We're looking at every edge at most once, yeah.
So is this count yesterday or was this person?
Let's take a look at that, because that is certainly very interesting. So here we have each edge being processed only once, but we do need to query each edge as we find the new node. So basically this turns into something that's based on, yeah, the number of edges. So it is a very efficient algorithm for this one problem. Unfortunately, it doesn't really scale all that effectively if you want to find an all pairs. I did mention this a little bit before, but that is one of the main downsides of Dijkstra's is it doesn't handle negative weights or cycles, particularly if it can handle positive weight cycles, but it cannot handle any negative weight cycles or cycles with a negative edge component. Any negative edge component is bad. But the best way to get from every vertex to every other vertex turns out to not be Dijkstra's or even that related to Dijkstra's. It's its own separate algorithm that you will see eventually. So this is something, again, that is covered in algorithms in about the same level of detail that I've gone over it here. I just wanted to go over it because graphs are a very important data structure, and in the course titled Data Structures, I want to give an overview of the most commonly used data structures so that you are aware of them. It turns out that graphs have a lot more algorithms related to them. So Dijkstra's, for instance, is an algorithm over the graph data structure, but the algorithms class will be exploring in a lot more detail what more algorithms can we use for certain common situations that we might see. And then also what are the algorithmic classes or approaches that you might use when you have some question and you want to answer that question with some custom algorithm. You can start to use the concept of a greedy algorithm, where you're going to say what looks like the best for my current situation. I'm going to assume that and run with it. Sometimes you can show that greedy algorithms give you the optimal result. Sometimes you can shave off a ton of time from the optimal result by taking a greedy approach. And then you can also show that the worst case is that this greedy approach returns something that's twice as bad as the optimal result. And you can place a bound on how good or bad the answer ends up being from that, then you can use that to your benefit as a time saver, or you can start to ask whether that trade-off is worth it or not. You'll also explore dynamic programming. So what is it like to store partial results as you compute, and then use that as a lookup table to make sure that you're not repeating work. We talked about this a little bit when we talked about recursion, and especially with regards to Fibonacci, recalculating and recalculating small values of Fibonacci numbers. And if you could store those in a table, you could drastically reduce the runtime. So algorithms will also cover things like that. What is dynamic programming? When do you use it? And there will be plenty of opportunities in later computer science classes to actually use these algorithmic approaches. So for instance, I teach compilers. The two main projects in compilers are both dynamic programming problems. So you will start to see these processes and start to use them in later courses. So it's a brief introduction to algorithms. You'll get into computational complexity in a lot more detail. In algorithms, I wasn't required to talk about it too much in data structures, but I like to at least give you a head start on that because there are a few methods that I haven't talked about that make your life a little bit easier when talking about recurrence relations. Yeah, it's a great class. The other thing you will learn is balancing binary search trees. So we talked about the insertion and deletion process with regards to a binary search tree, but it turns out that the way that we've implemented it is no better than a linked list in the worst case. So how do we make sure that we get that nice logarithmic guarantee of a tree we know that the depth of the tree should be logarithmically proportional to the number of nodes that are stored in it. How do we ensure that? It has to be something that we do when we add or when we delete, but the question now is, after how many adds or removes do we need to balance the tree? When do we know if the tree is out of balance? There are a couple different approaches to this. One that does it every single time, checks every insertion or deletion, and another, it just keeps track of a certain property of the tree and then makes a change as needed. That's the typical one that we cover in algorithms, but if you take it from me next winter, then I will probably dive into both and talk about the pros and cons of each. ABL versus red black. So this basically marks the end of the actual content for my own data structures. Graphs was optional. That is not typically covered in the class, but I decided to at least go through it because it's important. But I want to start talking about the next most important thing from your perspective, where there is absolutely no preparation in our typical curriculum, and I hate it. And that is interviewing. This is something that I think computer scientists in general don't have a lot of experience with, and as a lot of us are awkward introverts, myself included, it's very useful to have some guidelines for how to prepare and how to make an impression in an interview. What to think about, how to prepare, and then how to handle it. So let's talk about interviewing within the computer science industry, because it is very different from interviewing in other industries. And so general interviewing tips, while useful and part of this, are not everything you need to think of. We'll start with just a few minutes of motivation and probably have to come back to this tomorrow, but we'll start. A student who is through data structures is at a point where now you can land internships. Companies are interested in you now. You have the level of skills where you can be useful in a guided role. Why consider internships in the middle of a very busy undergraduate degree? Because this is one of the main ways to get a job in today's field. And I will preface this by saying the job market really sucks right now. So landing an internship is really the first step to being the top applicant for a full-time position after you are done. You become a known quantity when you interview. From an interviewer's perspective, a prospective employee is completely unknown. We don't know your behavioral standards. We don't know your work ethic. You have some things that you put on your resume, but what does that really mean? There's a GPA associated. What does that mean? You got a degree. What does that really mean? What is your skill level? Are you easy to work with? Are you easy to train? Do you have an open mind to learning new things, or are you stuck in your ways? These kinds of questions really help an interviewer be confident in their hire. But how much can you reasonably glean in a couple hours of an interview? Even if you come back for 3 or 4 different interviews, how much can you reasonably know about an applicant? If you've interned with them for a number of weeks, they're going to know much more about you than about any other applicant that might be applying for that position, which will immediately give you an edge. Assuming that you prioritize the right things in your internship, like showing your work ethic, like showing that you're open to learning new things. So one great way to get paid over the summer, you would at least be being paid comparable to any other position that you would get over the summer. And you would be doing relevant work that you can throw on your resume that would be useful for your eventual career. It is one thing to have a job to pay the bills. It's another to have a job that sets you up for future success in the field that you want to be in. Even if it doesn't lead to a permanent position, it's a way to get the skills and see the applications of how are what you have seen in your classes being used in industry. Yeah.
It's a value grab to say that often when I'm hiring somebody, I look for, they've had an internship. I'll call them before I'll call a previous job, because a lot of times,
Yeah,
fresh out of college, the previous work has nothing to do with what they do.
Yeah.
But they did an internship, so if it's not a place that's where they want to get their job, I'll call them, I don't care about how they do the components.
Yeah.
I care about their experience at the internship.
Yeah.
That's way more valuable.
absolutely. So networking while you're in an internship is also extremely important. Get to know the people you are working with. They are future references for you. If someone calls them, they can produce letters of recommendation for those jobs. That's very useful. So we can talk about a little bit about the interview process. In today's day and age, you're usually going through a screening interview, a behavioral interview, a technical interview. You go through a long process to get there. But in most places, the largest component of this is actually going to be the technical interview. So you will see some kind of algorithmic or coding problem, and you need to be prepared for a complete unknown problem that you will need to solve. The reason they give this to you is to try to understand your process. It's not binary, can you solve this or not? It is, how do you tackle a problem that is thrown at you that you are probably not 100% prepared to solve? It should be similar to things you've seen before. Maybe it utilizes some algorithmic technique that you've seen in some class, but it's been a little while. But being able to apply that to this problem, or even identifying this looks like a dynamic programming problem. I'm going to take a dynamic programming approach to this. Even saying something like that shows that you can start thinking about the problem in the right way. So don't think about the number of problems you get through or how fast you solve something. They're not particularly interested in that. They want to understand your thought process. So because of that, you need to be vocal as you are solving the problem. You should be talking about what you are thinking about, what you are doing, any ideas you have that you're not implementing. I'm thinking that I could use this, but it seems like that's going to be too slow for any of that process is going to really help you to, or help them to understand your process. So talk out loud, ask clarifying questions. If you don't understand something, or you think that I understand it, but I'm 95% sure, just clarify. They won't hold it against you to clarify, and in fact, that shows a positive personality trait. That when you're uncertain about something, you don't make assumptions, you will make sure that you're doing it right before you start implementing something wrong. If someone interjects, that's not necessarily a bad thing. Maybe they're just providing some extra clarity or nudging you in a direction where they want to see your thought process after you've gone down that direction. So let them help you. Gosh, we are over time. This is unfortunate. I start to have really a lot of fun when I start talking about interviewing because it's not the same set of skills, but we'll come back to this tomorrow and do this in a lot more detail. Yeah.
You guys post optional percent?
Yes, as we are now through everything, optional homework is going up and I'll figure out when to make it due. Sometime next week.
Okay, well, yeah.